Hi everyone, in this video we can discuss about counter circuits. These counters are exactly like our registers that we have already seen, and these counters are used for counting application. It's very important in our digital systems, and we can use it for counting like 0, 1, 2, 3 in ascending order as well as in descending order. Sometimes we can design certain counters for counting in a different pattern, given patterns. Okay, so basically we have different types of counters. Generally we can classify these counters as asynchronous counters as well as synchronous counters. Two types of counters. So here we need to learn how to design asynchronous counters and how to design synchronous counters and what is the difference of these two. Okay, so this is asynchronous counters, we can call it as serial counters. And another way, this synchronous counters, it has one more name, that is ripple counter. Okay, this is based on this implementation. Okay, another counter is synchronous counter, we can call it as parallel counters. Synchronous counters or parallel counters. But asynchronous counters, we can call this asynchronous counters as serial counter or ripple counters. Why it is ripple? Because suppose this is a 2-bit asynchronous counter. 2-bit means that counter that contains two different flip-flops, and the first flip-flop and the second flip-flop. The first flip-flop is triggered by an external clock and its Q output, sometimes the Q bar output, will trigger the second. Okay, so the first one is triggered by an external clock, second one is triggered by the output of first flip-flop. Suppose it is a 3-bit asynchronous counter and we have one more flip-flop here, then this will triggered by the output, sometimes the Q or Q bar sometimes. Okay, the output of second will trigger the third. See, so the value, whatever value is available in the input of that first flip-flop, it will comes here after applying that external clock pulse, and that will come to the next flip-flop after changing the output of first flip-flop, because this will act as the clock of second, and this will trigger the third. So this is like a wave, one will trigger the next, just like our wave in our sea. That is why it is named it as ripple counter. So asynchronous counter is also known as ripple counter, because this change, the variation in the output will propagate in a ripple fashion. That is why it is ripple counter. And what about our synchronous or parallel counter? Synchronous or parallel counter means, suppose this is a 2-bit synchronous or 2-bit parallel counter. That means it will contains two different flip-flops. And what is the difference of a synchronous counter? In synchronous counter, the same external clock pulse simultaneously trigger the two flip-flops. Suppose this is a 3-bit synchronous counter, then total we have 3 different flip-flops, and the entire 3 flip-flops simultaneously triggered by the same external clock pulse. What is the difference? Here the output will change simultaneously by changing the external single clock pulse. The output will reflect, the change will reflect in the output after changing the single clock pulse. Okay, so this is parallel or synchronous counter. This is a basic structure, and this is a synchronous counter, the basic structure. We can also call this asynchronous counters as ripple counter because of this ripple way of operation. One more, we can call this kind of counters using number of bits it can represent. Number of bit it can use. Here it is 3 flip-flop, so we can call it as 3-bit counter. Another way, using 3-bit, how many different patterns are possible? how many different binary patterns are possible with 3 bit? 2 to the power 3, that is 8 combination. So we can also call it as mode 8 counter, mode 8 asynchronous, or mode 8 triple counter, or 3 bit asynchronous counter. Both are same. Suppose this one is not here, then we can call it as this is 2 bit counter. Or using 2 bit total, how many different binary patterns are possible? 4. So we can call it as mode 4 counter. Both are same. The same name convention we can also apply for the synchronous counters. In case of synchronous counters, here it is 3 bit synchronous counter, because 3 flip-flops are there and it can store 3 different bits at a time. So this is 3 bit synchronous counter. Using 3 bit, it can represent total 2 to the power 3, 8 bits. That means this is mode 8 counters, mode 8 synchronous counter. Suppose this one is not there, that means 2 flip-flops. 2 flip-flop means it can represent 2 bits at a time. So this is 2 bit synchronous counter. 2 bit synchronous counter means 2 to the power 2. It can represent 4 different binary pattern at a time. So we can call it as mode 4 synchronous counter. Okay, then we can let's discuss about the design and implementation of asynchronous counters, or the ripple counters. Okay, so let's see this. This is actually a 2 bit synchronous counter. 2 bit asynchronous counter. We can also call it as 2 bit ripple counter. And in another way, 2 bit means it can represent 2 to the power 2 for different patterns, binary patterns. So the same we can call in another name like mode 4 asynchronous counter, or mode 4 ripple counter. And again, this structure is actually indicating up counting. Okay, this is up counting. That means it will count in ascending order, like this is mode 4, so it will count 4 different modes like 0, 1, 2, 3 for different stage, and will repeat the same pattern like 0, 1, 2, 3. Okay, so this is the case or functionality of your mode 4 up counter. Okay, so this is the structure, and this is a JK flip-flop based implementation. 2 flip-flops are there. First one is this, and second one this one. See that connection J and K connected, keep it as high always. Here also J and K input of these second flip-flop also keep it high, because J and K equal to high means it will always toggle. Okay, so one external clock connection is applied to the first flip-flop, and the output of this one considered as a clock to next flip-flop. And again, this one is one output, and this one is one output, one bit of output. So this is Q0, Q1. So we can represent this like J0, K0. This is your Q0 output. This is a complement form of your output. This is J1, K1. This is Q1, Q1 complement. Okay. So see, in asynchronous counter, which flip-flop is connected with that external clock pulse, that particular flip-flop will generate always that lowest significant bit, least significant bit of your result. Okay, this is a property that is valid only in case of asynchronous counters, only in asynchronous counters or in ripple counters. Which flip-flop is connected with that external clock pulse, that flip-flop is going to generate that LSB bit of your binary pattern. So that output is in the form Q1, Q0. Because Q0 is generated by this flip-flop, this flip-flop is connected with the clock, and its next bit is generated by this one. That is why Q1, Q0. So the pattern will be like 0, 0 for 0, 0, 1 for 1, 1, 0 indicate decimal 2, then 1, 1 means 3. After counting in ascending order like 0, 1, 2, 3, it will repeat the pattern again like 0, 1, 2, 3 and so on. Okay, so keep it in your mind. Which flip-flop is connected with that external clock pulse that will generate that least bit of your result. This is valid only in case of asynchronous counters or in ripple counter. Okay, this is not possible. We can't directly predict which flip-flop is going to generate which bit in case of synchronous counters. And synchronous counters we can't predict which flip-flop is going to generate which bit of your result. Okay, we can directly predict or we can directly identify from that block diagram in case of synchronous. But in case of asynchronous counters, we can predict which flip-flop is going to generate your LSB bit, next LSB bit and so on. Because that clock pulse which is connecting with this flip-flop here, so this flip-flop going to generate the least significant bit of your result, and the next flip-flop which is triggered by the output of this first flip-flop going to generate second LSB bit and so on. Okay, and this is the timing diagram. So consider this is negative edge triggering. So all the negative, this is that this one actually indicate that external clock pulse. So this will going to trigger your first flip-flop which is directly connecting with that external clock pulse. Its output is going to act as a clock for second flip-flop. Okay, so Q0, this is triggered by this external clock, and here we are assuming negative edge triggering. Negative edge triggering actually indicated by this bubble and arrow. Bubble and arrow indicate negative edge triggering like this. Clock representation like this. Bubble and arrow is indication for negative edge triggering. Without bubble, direct arrow indicate positive edge triggering. Okay, these are some valid basic points that you have to understand in order to identify or analyze the block diagram of your counters. Okay, so this external clock pulse is going to trigger this flip-flop. So, and we are assuming negative edge triggering. So, initially assume your Q0 is preset to 0. Okay, so whenever this happens, the negative edge of your external clock will happen, that toggling happen here in Q0, because here J and K both set to high. J and K equal to high means it will toggle. So the 0 will toggle to high during the negative edge of that first clock pulse. So it will retain in the high state till the negative edge of your second clock pulse. During the negative edge of your second clock pulse, the Q0 again toggle. Toggling means now it is in high, so toggling means it will come back to 0. And it retain to that 0 state till this point, because this is the point where the third negative edge of your third clock pulse will happen here. And during this point, during this negative edge, that Q0 again toggle. Now it is in 0, toggling means come back to high. And during the negative edge, again it toggle, that means come from high to low. This is Q0. Okay, so this external clock pulse will trigger only this particular flip-flop, that will affect, the result will affect only that Q0 output. And what is the next case? This Q0 is acting as a clock for your second one. So, and we are assuming negative edge triggering. What is the meaning? The negative edge of your Q0 will trigger this flip-flop, and that result will reflect here. That means the Q1 will toggle during negative edge of your Q0. Clear? So, Now we don't need to consider this external clock pulse. It's already done for this Q0. Now we need to consider the negative edge of your Q0. That external clock pulse trigger only that first flip-flop, and that result is represented here like this. This Q0 is going to trigger your next flip-flop, so we need to consider negative edge of your Q0 here, and this negative edge of Q0 will trigger your next flip-flop, and the corresponding result will happen here in Q1. Okay, so assume that Q1 is initially set to 0, cleared initially. So whenever the negative edge of your Q0 happen, at this point this Q1 toggle. Q1 toggle means, why it is toggling? Because J and K both set to high. J and K equal to high means this is the case for toggling. So during the negative edge of your Q0, the Q1 will toggle. Here it is 0, so toggling means it will come from 0 to high, and it will retain the high stage till next negative edge. Negative edge of Q0. During the next negative edge of Q0, again Q1 toggle. Toggling means it is in high state, so it will come back to 0. See, so this is the timing diagram of Q1. And see, what is the meaning of this pattern? So we need to check the value at different clock pulses. This is first clock pulse. This is second clock pulse. This is third clock pulse. This is fourth clock pulse. And this is fifth one. Okay, see, in first clock pulse, what is the pattern? Q1, see, how can we represent? Q1 Q0 order. Why it is Q1 Q0 order? Q0 should be your LSB, because this is the flip-flop which is directly connected with external clock pulse. That particular flip-flop going to generate what? That LSB bit. This is Q1. Okay, so you can represent like this, Q0 and next Q1. Okay, so during the first clock pulse, see, Q1 is 0, Q0 is 0. Both are in low state. So the pattern is 0, 0. And what about second clock pulse? In the second clock pulse, see, Q0 is 0, low state, and sorry, Q1 is 0 and Q0 is in 1 state. So this is 0, 1. In third clock pulse, see, Q1 is 1 and Q0 is in low state, 0. That means this is of the form 1, 0. Okay, then what about fourth clock pulse? Fourth clock pulse, both are in 1, 1, 1. What is it? This is equivalent to decimal 0, decimal 1, 2, 3. This will count in upward direction, 0, 1, 2, 3. See, in fifth clock pulse, what is the stage? This is in low stage. This is in low stage. That is Q1 and 0, Q0 is 0. So after 0, 1, 2, 3, it will repeat the pattern again like 0, 1, 2, 3. Okay, so this is the structure of a 2-bit up counter, asynchronous up counter, or 2-bit ripple counter, 2-bit up counter, asynchronous or ripple counter. Okay, now we can consider 3-bit asynchronous up counter. So this is the structure. Again, here we are assuming negative edge triggering. So this particular flip-flop is connected with, we can mark it as JAKA, and this one is connected with external clock pulse. So this is going to generate the least significant result of your least significant bit of your 3-bit result. And this one is triggering this particular flip-flop. We can mark it as JBKB. This is going to generate second LSB bit. of your third bit output, and this is triggered by this one, so we can mark it as JCKC. This one is going to generate next bit of your result. Total three bits CBA form. So how many patterns are possible? Using 3 bit 2 to the power 3, 8 different possibilities are there. So we can also call it as mode 8 counter. Both are same. 3-bit ripple counter or mode 8 ripple counter, 3-bit asynchronous counter or mode 8 asynchronous counter, all are the same. So what are the possibilities? See, A, B, C. What are the patterns that are going to generate? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 till 1, 1, 1. 0 to 7, total 8 different state. After that, it will repeat the pattern like 0, 0, 0, 0, 0, 1 again. Okay. So what is the meaning of this clock cycle? Here, see that clock representation bubble and arrow means we are assuming negative edge triggering. So this particular flip-flop output is generated based on the negative edge of your clock, external clock. So which one? A. The A output depends on negative edge of your external clock. See, during the negative edge of that external clock pulse, A will toggle. Both J and K of the 3 flip-flop connected with high stage or BCC means it will always toggle. So here it toggle. This is toggling high to low, again low to high, high to low, low to high, high to low, low to high, high to low, low to high, high to low during all the negative edges of your external clock pulse. Okay, now the output A from the clock of your second flip-flop means negative edge of your A trigger this particular flip-flop. So we will toggle during negative edge of your, we will toggle during the negative edge of your A. So we have already finished this A, timing diagram of A. So we can consider negative edge of your A. This is the triggering for next flip-flop. So see, initially B is assumed to be 0 state, in 0 state, and during the negative edge of A, B will toggle low to high, high to low, low to high, high to low, low to high. Okay. This triggering will happen during negative edge of your output A. Now, here we have one more third bit, that is C bit. So C is going to generate by, C is going to generate by this flip-flop. This is triggered by the output B. So we need to consider negative edge of your B output. We have already marked the clock pulse or timing diagram of B. So during the negative edge of B, the C will toggle. So initially assume C in 0 state. During the negative edge of B, this will toggle. Low to high. Here it is high to low. So see the patterns. The first clock pulse. So this one, low state and high state till this point. This is first clock pulse. See, all are in low state. 0, 0, 0. And in the next clock pulse, this is high, 0, 0, 0, 0, 1. And in third clock pulse, this is 0, this is 1, 0. That means 0, 1, 0. This one, 2. And in next clock pulse, see, 0. Here it is 0. 1, 1. The next binary pattern. Next, here, this is 1, 0, 0. This one equal to 4. And in next clock pulse, this is 1, 0, 1. This one. And in next clock pulse, 1, 1 0 1 1 0. And in next clock pulse, this is full of 1 1 1 1. Okay, and in next clock pulse, after this 8th pattern 1 1 1, see this case, here it is again full of 0 0 0, and after that this is 0 0 1. So after the 7th state it will repeat the pattern. Okay, so this is again up counter, 3-bit up counter or mode 8 up counter in asynchronous fashion or in ripple fashion. Now we can consider this particular implementation, that is, this is an IC, this is the block diagram representation for this particular IC. This particular IC will act as mode 8 or mode 16. This is a circuit implementation. Sometimes it will act as mode 8 fashion or it will work in mode 16 fashion based on the clock pulse. See, these are 4. Mode 8 means 3-bit, mode 16 means 4-bit. It will generate total 16 state, it will generate 8 different state, and here it is clear input. This one indicate that clear input. This is that clear representation in particular in this particular IC. And here we have 2 different clock pulses. Okay, so basically it is 4-bit upcounting fashion, and whenever the clock pulse is applying to here, external clock pulse is applying to here, this particular flip-flop is inactive and it will generate only 3 different bit of output. That means it will generate total 2 to the power 3, 8 different patterns. Okay, so in other way, suppose we are going to apply that connect that clock pulse with this connection. All the 4 flip-flops are active in this state, and it will generate 4 different output patterns. 4 output pattern means 2 to the power 4. It will generate 16 different states. That means it will act in mode 16 asynchronous count fashion. This is again up counting. Okay, so this is the timing diagram corresponding to this particular IC or 4-bit up counting. Again, we can consider in negative edge triggering. So this is the negative edge of your external clock pulse. You can consider that mode 16 or 4-bit counting. So during this, which flip-flop is connected with that external clock pulse? That A, right? So this will form our LSB. Okay, so this will toggle during negative edge of your external clock pulse. Here it is toggled. Again is toggled during the negative edge of your clock pulse. Here again, and so on. And this will trigger your B flip-flop. It will trigger your B flip-flop. Okay, so the negative edge of this, negative edge of your QA output will trigger your B. See, initially it is an 0, and during the negative edge it will toggle. Again it toggle, toggle and toggle, and so on. And this will trigger the flip-flop C. So during the negative edge of your QB output, negative edge of your QB output, QC will toggle. Initially it is assumed to be in 0 state, so it will toggle, again it will toggle, and so on. This C flip-flop will trigger, the QC output will trigger the D flip-flop. So during the negative edge of your QC, this one, again this one, QD will toggle. It will retain in that 0 state initially, and during the negative edge of QC it will toggle. See the pattern. Initially it is the first clock pulse, it is 0 0 0 0. Next it is 0 0 0 1. Next it is 0 0 1 0. In the next clock pulse it is 0 0 1 1. Next it is 0 1 0 0 and so on, and finally it is full of 1 1 1 1, and it will repeat the pattern. Okay, this is the case of mode 16 asynchronous up counter or 4-bit asynchronous up counter. We can also call it as ripple counter or serial counter. Okay, next is about down counting. This will count like this, like 3 2 1 0, again 3 2 1 0, descending order of counting. Okay, so how can we change this circuit for down counting, asynchronous down counting? So in our previous case, we have considered that Q output as clock to the next flip-flop. All others are same. We need to keep both J and K as high. And first one here, it is connected with external clock pulse. Instead of connecting that Q as clock to next, here we need to take Q bar of your first flip-flop as clock to next. Then it will act as down counter. All the other connections are the same, like your down up counting, and in order to convert this into down counting fashion, you have to change the clock. Instead of considering this Q0 as the clock of this flip-flop, you need to consider the Q bar output of this first flip-flop as the clock of your next one. Then it will work as down counting. Down counter. Consider this, that external clock pulse, and here again we are considering negative edge triggering. So during the negative edge, the first flip-flop will trigger like this, 0 to high, 0 to high to 0, again 0 to high, high to 0, 0 to high, high to 0, and so on. See, here this Q is not going to trigger your next flip-flop. Instead, Q bar output of the first is going to trigger. So this is not the clock pulse of Q. Q0 is not directly going to trigger next. So you need to draw Q bar. What is Q bar? You need to draw the timing diagram of Q bar next. From this Q0, this is the timing diagram of your Q0. So you need to take the complement of this, like wherever it is low, you have to mark high here in Q0. If Q0 is high, you need to mark it as low. Here it is low, so Q0 should be high. So just draw the complemented form of your Q0, that will be Q0 complement. This is going to trigger your next flip-flop. So the negative edge of your Q0 bar, this is negative edge triggering method. So the negative edge of your Q0 bar is going to trigger your next flip-flop. So this is the difference in down counting. Instead of triggering by Q0, here it is triggered by Q0 bar. So in the timing diagram, you have to plot the Q0 first and draw the timing diagram of Q0 bar. How to draw the timing diagram of Q0 bar? Just to complement this Q0. If it is low here, you should draw high here. If it is high, then you should draw low here. And mark the negative or edge of your Q0 bar. That is going to trigger your next flip-flop. See, during the negative edge of Q0 bar, Q1 will trigger. This is toggle. Again, during the negative edge of your Q0 bar, it will toggle. Okay, and see the pattern. What are the output? Output is always Q1 and Q0. Q0 complement has no meaning in output, but that Q0 bar is going to trigger your next flip-flop, second flip-flop, right? So, in order to consider the clock pulse, you have to consider Q0 bar. But that output pattern is exactly like your up counting Q1 and Q0. In the first clock pulse, Q1 is 0, Q0 is See, initially it is full of 0. Initially both are 0, right? Initially both are 0. It is cleared or preset to 0. And in the next clock pulse, see, in the next external clock pulse, during this time, this clock time, Q0 is high, Q0 is high, see Q1 also high. This is like this. Sorry. Both equal to 1. And in the next clock pulse, see here, this is 0 and this is 1. That is 1 0 here. This is 1 0 and next it is 0 1, next it is 0 0. That is 3. Here it is see, here it is 3 2 1 0 and we'll repeat the pattern. Okay, so this is about down counting, 2-bit down counting or mode for down counting using asynchronous counter or ripple counter. See, this is a 3-bit down counter or mode 8 down counter using asynchronous mode of implementation or ripple counter. 3-bit ripple counter, 3-bit ripple down counter or 3-bit asynchronous down counter. Okay, this is the structure. This A is connected with external clock. A bar is triggering the next flip-flop B. B bar output is triggering the next flip-flop C. And all the J and K inputs are connected with high, means all the flip-flops will trigger during, see here it is negative edge triggering representation. So during the clock, negative edge of the clock pulse, all the flip-flop will toggle because J and K kept it as high always. Okay, and A, B, C are that output pattern, and the first one, the flip-flop which is connected with the external clock pulse, it is going to generate the least significant bit. So that is by A here, next B, because B is triggered by this one, the first flip-flop. So B form the second LSB bit and C next. So these are the all possible combination in descending order 7 6 5 4 3 2 1 0, and it will repeat in 7 6 5 4 3 2 1 0 fashion. So this is the timing diagram. So based on the negative edge of external clock pulse, A is going to trigger, and here B and C output is directly given here. It is not easy for you to understand, so follow this one. See, here it is. This one is actually your external clock pulse. Based on that external clock pulse negative edge, the output A will toggle. So A is toggling during negative edge cycle of your external clock pulse. And here it is down counting, so instead of A bar output is going to trigger your next flip-flop B. So you have to plot that A bar first, then it will be clear for you. This is A, just take the complement of your A. That is, you have this timing diagram for A here. Here it is 0 means you have to draw high in case of A complement. Here it is high means you have to mark low here. Just take the complement. So here it is A complement. A complement's negative edge going to trigger B output, B flip-flop. So during the negative edge of A complement, B will trigger, B will toggle. Here it's toggled, again here it's toggled again. During the negative edge of your A complement, it will toggle again, like this. And again you have to mark B complement, because instead of B complement output of second flip-flop is going to trigger third flip-flop. So here B is 0, you have to mark high here, and here it is high means you have to mark 0 in case of B complement. Just take the complement of B and draw the timing diagram for B complement and mark the negative edge of B complement like this. During the negative edge of your B complement, C going to trigger. So here initially it is 0. During the negative edge of B complement, it will toggle. See here and here. So what are the patterns? Initially, during the first clock pulse, first external clock pulse, A is 0, B is 0, C is 0. So 0, 0, 0. During the next clock pulse, what is the pattern? C is 1, B is 1, A is 1. 1, 1, 1. In the next external clock pulse, here 1, 1, 0. In the next external clock pulse, here it is 1, 0, 1. This is 5. Next is 1, 0, 0, 4. Next is 0, 1, 1, 3. 0, 1, 0. 0, 0, 1. 0, 0, 0. So you have to plot A complement from A, B complement from B, and try to plot that A output timing diagram, B output timing diagram as well as C. Then it will be clear for you. This is the timing diagram for 3-bit asynchronous down counter. Okay, thank you.